Have you ever really stopped to wonder how massive, distributed applications actually manage to handle incredibly complex data flows reliably, even when machines crash and networks just completely fail? Well, today we're decoding the architecture of resilience. Think about the sheer volume of digital transactions happening right this very second across the globe. We rely on these systems to be flawless, right? Yet under the hood, the infrastructure powering them is inherently chaotic. Hardware fails, network connections drop, processes panic, and suddenly restart. In this explainer, we'll be analyzing exactly how we encode and transmit data between different processes, moving way beyond simple databases to look at durable execution, event-driven architectures, and the fundamental modes of a synchronous data flow. Okay, let's dive into this and explore exactly how modern software survives the unpredictable. So, here's our roadmap for today. First, the partial failure problem. Second, workflows and durable execution. Third, the rules of determinism. Fourth, event-driven architectures. Fifth, the actor model. And sixth, a modes of data flow summary. Okay, section 1, the partial failure problem. Picture this. You're processing a customer's payment. Your code successfully reaches out to a credit card service and boom, the customer's card is debited. But right at that exact millisecond, right before your code can call the banking service to actually deposit those funds into the merchant's account, the machine running your application loses power and crashes. So what happens? The customer has absolutely been charged, but the merchant hasn't been paid. The money is just stuck in digital limbo. This right here is the essence of a partial failure in a distributed system. It's an absolute nightmare scenario that causes immense panic for developers, and as you can imagine, generates some pretty furious customer support tickets. And honestly, here's the scariest part. In massive cloud environments, micro outages, network blips, and silent machine restarts, they don't just happen occasionally, they happen thousands of times a day. Handling these failures gracefully is literally one of the most critical challenges in software design today. When you map out the sequence of steps for a standard payment, it reveals a pretty massive vulnerability. You start with a payment request, you compute a fraud risk score, debit the credit card, and finally, you credit the bank account. Now, in a traditional, single database monolithic architecture, solving this is actually super easy. We just wrap all those updates in a single database transaction. It's an all-or-nothing operation. If something breaks halfway through, the database automatically rolls back everything, acting as if the transaction never even started in the first place. But in modern architectures, we really can't do that. We're constantly interacting with external, third-party services over a network, a fraud detector API, a credit card gateway, a banking network. We simply can't wrap external network calls in a local database transaction. And because networks are inherently unreliable, we face this constant risk of failing partway through our graph of tasks. We desperately need a completely different mechanism to guarantee that our complex workflows execute exactly once, no matter what breaks.
Moving on to section 2, workflows and durable execution.
Frameworks like Temporal and Restate step in here, and they provide what's known as durable execution. Honestly, they're the architectural heroes that provide exactly once semantics for these incredibly complex multi-step workflows. The way they achieve this is totally fascinating. Behind the scenes, these frameworks rely on highly reliable durable storage, specifically using something called a write-ahead log. Imagine you're debugging a program step by step. The workflow engine acts exactly like that. Every single time your workflow is about to make an RPC, a remote procedure call, to another service, the framework literally writes a note in its log, saying, okay, I'm about to do X. Once the call succeeds, it writes X succeeded, and here is the result. Now, let's say the machine just catches fire and crashes. The workflow engine simply restarts the task on a completely different healthy machine. It replays the execution from the very beginning of your code. But here's where the magic happens. As it runs down the lines of code, it checks its write-ahead log. When it encounters an RPC call that was already successfully logged before the crash, it skips making the actual network call all over again. It effectively stubs or mocks the call, pretending it reached out to the network and simply returns the previously recorded result from the log. It remembers its place perfectly, skipping the parts it already finished and picking up exactly where it left off.
Which brings us to section 3, the rules of determinism.
Now, because durable execution relies entirely on replaying code from the top to recover from a crash, that code must be perfectly predictable. Let's sharply contrast deterministic code with non-deterministic code. Deterministic code always produces the exact same outputs from the exact same inputs. If you run it a million times, it takes the exact same path. Non-deterministic code, on the other hand, might do something slightly different every time it runs. Just imagine your workflow has an if statement that branches based on the current system time, or maybe it generates a random number to decide what to do next. During the original run, the random number might have been a 5, so it took branch A and logged those steps. But during a crash recovery replay, the random number generated might be a 2, telling the code to take branch B. The framework will look at its log, see that branch A was supposed to happen, realize the code is now asking to do something completely different, and it will just panic and break. This makes workflow code highly sensitive.
So to handle these inevitable replays safely, external APIs must be idempotent. Idempotence is just a highly technical word for a very simple, universally understood concept, mashing the call elevator button. We've all done it right. If you walk up to an elevator and push the button once, the elevator is called. If you impatiently mash the button 5 more times, it doesn't magically summon 5 different elevators to your floor. The system registers your intent once, and subsequent identical requests just have no additional effect. When we're dealing with APIs, if our workflow engine crashes and restarts, it might accidentally retry a network call that actually succeeded right before the crash, but where the acknowledgement was lost over the network. To absolutely prevent charging a customer twice, we must design the system to use unique transaction IDs for these API calls. The external service sees that unique ID, recognizes it has already processed that exact request, and simply acknowledges it again without debiting the card a second time.
All right, Section 4, Event-Driven Architectures. So far, we've really only looked at services calling each other directly. Let's switch gears and explore an alternative paradigm, asynchronous dataflow. In an event-driven architecture, a request is called an event, or sometimes a message. And crucially, these events usually aren't sent directly to the recipient. They go through an intermediary, known as a message broker, which you might also hear called an event broker or a message queue. To really understand this shift, contrast a phone call with the postal service. Direct APIs are exactly like a phone call. Both people have to be available at the exact same time, actively listening and responding. A message broker? That's like the postal service. You write your letter, drop it in the mailbox, and you just walk away. You completely trust that the intermediary will safely hold on to that message and eventually deliver it to the recipient, even if they aren't home right now. The difference between a tightly coupled synchronous RPC and a loosely coupled asynchronous event stream is profound. It's a real game changer. In an RPC architecture, the client sends a request and is forced to just sit there, waiting blockingly for the server to process it and send a response back. But with asynchronous events, the sender just encodes the event, fires it off to the message broker, and completely forgets about it. It immediately moves on to its next task. The recipient pulls the message from the broker whenever it actually has capacity. This introduces a massive architectural superpower, back pressure. Imagine it's Black Friday. Traffic spikes tenfold. In an RPC system, the servers just get overwhelmed, they time out, and they crash. But in an event-driven system, the sender fires off millions of purchase events, and the message broker safely buffers all of them. The downstream recipient services might fall a few minutes behind, sure, but they won't crash. They just pull messages at their own maximum speed until they eventually catch up.
Section 5, the actor model. The actor model is a specialized programming paradigm that takes these asynchronous messaging concepts and applies them strictly for concurrency within a single process. Normally, dealing with multiple threads accessing the exact same data in memory is a massive headache. We're talking race conditions, complex locking mechanisms, deadlocks, the whole shebang. The actor model beautifully solves this by encapsulating logic into individual, completely isolated entities called actors. You might have one actor representing a specific user's shopping cart, for instance. Crucially, an actor has its own private, local state that is never, ever shared with any other actor. So how do they talk to each other? Exclusively by sending and receiving asynchronous messages. Every actor essentially has its own personal little mailbox. Messages arrive and queue up in that mailbox. The actor pulls out one message, processes it fully, updates its private state, and only then does it move to the next message. Because an actor only ever processes one message at a time, strictly sequentially, you completely eliminate the need for locks or thread synchronization. The framework schedules the actors under the hood, making it incredibly efficient. Though it is worth noting that in distributed actor frameworks spread across multiple machines, message delivery is not strictly guaranteed. In extreme network partitions, messages can still technically be lost.
And finally, Section 6, Modes of Dataflow Summary. Zooming out a bit, we can categorize the fundamental modes of how encoded data flows between processes. First up, databases. The process writing to the database encodes the data, and another process, or maybe the same process later on, decodes it. Conceptually, writing to a database is beautifully simple. It's literally like sending a message to your future self. Second, we have RPC and REST APIs. The client encodes a request, the server decodes it, computes something, and encodes a response, which the client then decodes. This is the synchronous network paradigm. It's highly conversational, but as we saw, tightly coupled.
And third, event-driven architectures, using brokers or actors. The sender encodes a message, and the recipient decodes it entirely asynchronously. Understanding these three modes isn't just academic trivia. Mastering how to encode and decode data across these paradigms dictates the entire architecture and resilience of the modern web. So, why do we actually care so much about these different modes, particularly the loose coupling of asynchronous architectures? Because it dictates the evolvability of your application. Choosing between direct network calls and event-driven models isn't just some technical quirk. It is a fundamental business decision. When senders and receivers don't have to be updated simultaneously because they're communicating via a broker, you can support true rolling upgrades. You can deploy a brand new version of a service to just 5% of your servers at a time with absolutely zero downtime. This decreases deployment risk immensely. Think about it. If a new release has a nasty bug, you catch it early on a tiny subset of traffic and roll it right back before it impacts your entire user base. It enables massive engineering teams to make frequent, small, independent releases rather than coordinating terrifying, company-wide weekend deployments. The mechanics of durable execution, idempotency, and message brokers are definitely not just abstract theories. They're the actual levers we pull to ensure our applications can survive the chaotic, totally failure-prone reality of distributed networks. Understanding this data flow is exactly what allows companies to scale gracefully without just collapsing under their own weight. So, I'll leave you with this final thought to ponder. How does the way we encode and transmit data fundamentally shape the maintainability and evolvability of our applications? Think about the digital tools you rely on every single day and the invisible architecture working tirelessly to keep them online. Keep exploring.